Ladies and gentlemen, quick round of applause for our next speaker. Boris will be telling us about optimizing large firewall rule sets.
Yep.
I'll be in the first row to troll you about it.
Thank you, Christoph. There are at least two reasons why it is the best thing to have an after party at the end of day one. Well, the first reason is obvious. It's always cool to have an after party. And the second one is not that obvious. I'm not standing between you guys and the after party, so I have some time and give you a good, neat explanation about Ipfw techniques. So, how many people in the room are familiar with Ipfw rule set? Just raise your hands. Okay, Ipfw lookup tables. Okay, and table arg from lookup tables. Oh, yeah, that's cool. So, I've submitted my work in April, and it's September now. So we've added 70 million rules on top of that. No breakage. We are running OK. So I had to change title a bit. This is about 1 million times bigger rule set than I wrote about 20 years ago when I was a student of physics department of Moscow State University. Back then, I started really hard to improve my rule set composition techniques. So, boom, and I'm a Yandex fellow. I'm working as a network foreman at Yandex. I manage a small team of network engineers that are responsible for every single network in our campus. In our warehouses, we control the management network for our data centers, and we do provide remote access to our corporate network as well. So let's take a look on the simplified diagram of our network. We have around 400 routers that are responsible for routing and filtering network access from users to the services of inside our corporate network and the internet, no matter if they are connected through the VPN or wireless or through wire. All of these servers are running FreeBSD. That is why actually I'm standing here. And this talk is a story about the firewall we are running on these servers, a story of dynamic firewall. So, what are the properties of this firewall, why we build it, and how we build it? The first thing, it limits the whole traffic from the users to every single network, either in corporate network or the internet. It's combined with the old services that are needed for the users, including DHCP server, array router advertisement for IPv6. We have a cache node for our internal streaming, etc., etc., etc. Another very important property is that sometimes we run these routers and firewalls on very low power and almost silent servers. So we need to keep our CPU footprint, CPU requirements and green power something, yeah, at very low levels. And the main reason why we call this firewall dynamic is that when a user connects to the network, the firewall is configured for processing the user's traffic within 3 seconds. Let's take a look on the access rules, how we do it, what is inside, and how we deal with it. An access rule for the dynamic firewall uses the user notation from the source, because initially we do not have any idea of what are the user IP addresses. The destination is usual. It's a network prefix or a domain name for the service, either on the corporate network or in the net. Let's talk about some challenges. These things arise. We still want to use per-user granularity. This is kind of a new thing to the techniques that is common for the enterprise firewalls. So we do support per user or per group rules of any amount of this. We do support the rule sets that are different if a user is connected through the VPN or through the wireless network within the offices. We have some sensitive services that we do not want to expose to the VPN. We do run IPv6, so we have a lot of IP addresses that are given out to users, and they change frequently. And one last but not the least, any user can roam to any office or switch to VPN network, and it is totally okay to have it everywhere he or she wants. So this is kind of another challenge to be solved. We need to cut some corners. The first corner we're going to cut, we do support UDP and TCP only. There is a way to support other protocols, but so far we haven't seen any demand for that. So TCP and UDP are enough, Most of the rules we have in our rule set are made for large groups, especially large groups like all staff members, and we will see how we deal with this to save some RAM and CPU usage. And another thing that we do not want all users to be loaded into firewall rule set. We can load them on demand, and when the user is disconnected, unload the rules from the kernel. Let's take a look on the groups we have at the high level of the rules. We combine users like staff, all the departments, or we can combine users based on their projects. Basically, we have couple more ways to group users into this kind of tree-view structure, and all of these groups are pretty much okay to be used in the rule set. Here's the sample rule we have in our database. The rule tells us that the user user one, has access to the dev server using SSH, HTTP, and HTTPS. And the %mark denotes that this is just a user. This is a group rule. It allows all the staff members to the DNS cache. And another rule is all about giving access for all the developers to some network for their project. In green, you see how the processor that is in charge of converting these rules into Ipfw unpacks these rules. Given that simple explanation, here's our numbers. We have about 50,000 of rules running in our kernel. We have 65,000 users, and it's growing, both rules and users. And if you combine the individual user accounts and the IP address destinations, you will get that number that was on the title. So 570 million of entries, firewall entries in the rule set. The first thing to fix is how we do conversion between user account that is in the rules and the IP address, because firewall is all about IP addresses and network traffic, not that users. To do that, we can use a thing that is called mark. It was integrated into FreeBSD kernel a couple of years ago, and this is basically very similar to FW mark you can take in Linux kernel, but we had added some tweaks for that. So this is a 32-bit number, unsigned. You can it is saved in an mboof tag for each packet. You can set it using Ipfw setMark action. You can make a check with a mark opcode. You can do a lookup in lookup tables for that. And the most valuable thing for me is every time you use mark, you can mask out some bits. So you can play with the mark as a bit field value. Another thing we need to use for our firewall is lookup tables. Lookup tables can have different keys. For example, we will be using address key and number key in this talk. There are different algorithms that are supporting different types of keys, and we use different value types. So when you do a lookup in table, then you can fetch a value from that, and that value will be used in table arg. This is basically why I asked about table arg in the beginning. So let's try to take these two parts together and configure our firewall, converting this sample rule to the way we can load it into the kernel. First thing we need to do, we need to create a table, and that table would help us to convert IP address into mark. In this example, we know that user 1 uses IP address ending with 0 once, and user 4 is using another one IP address. So we load it into the table. Now we have a table comprising 2 records. And what we can do, we can use setMark when looking up a source IP address in the packet processing, and then we are going to check it using the markup code. So far, so good, because this is the real Ipfw rule that you can install into the kernel. It will work. The problem is that you need a special tool or a special sidecar to track all user IP addresses and push these mappings into the kernel. For this, we've built a message queue. The publisher for the messages are Radix server, and there are only 2 different types of messages. Message type number 1, it's a new map, so user IP address and the way it is connected to the network. And the second message is a flashing IP address when the user is disconnected. So we are able to convert all these rules into the raw Ipfw format, but we have some issues there. So we have 50,000 rules. We have like 120 million of ORs when we are comparing marks. And this is not going to have to be loaded into the kernel. It's too big, it's too slow, and I don't like it. Besides that, Ipfw is rather slow when you're talking about adding or removing rules. And Well, there are only 65,000 of rule numbers, and we have like 50,000 rules already, and we want some spare numbers for our static firewall or to grow it. So let's take a look on another differential. It's in review state. So if you have any ideas or comments, just go to the fabricator and leave your opinion. I think we'll be merging it in a week or so. And that differential allows us to use 32-bit rule numbers. Yeah, it should be enough, at least for a couple of years. But still, evaluating these rules sequentially, one by one, it's not an option for us because it's way too slow. To cope with this, what we can do, we can create a per user rule set or per user rule number, push all the rules that are applicable for the user into its rule set, and that will give us a drop in rule set count to around 13,000. Let's take a look at how we do it. We've seen the first step on the previous slides. We do a lookup of the source IP address of the user, and we mark traffic with the mark assigned for each user as well. Then we need another table that is converting mark of the user into the rule number that hosts all the users' rules. Let's take a look on this. So we have two users now, two rules, and we are going to convert them into a Ipfw format. The rule set for user 1 is pretty much simple. We skip source IP address here. We denote an any here because we've checked source address when we were looking up mark. For the user 4, the rule set is a bit more bigger here. So two rules and as an example. And now we need a glue to forward or to drive the traffic check routine to these rule sets. For that, we create a number-to-number table. For the key, we use mark. For the value, we use skip to value, so the rule number of the user rule set. So far, so good? Okay. So we've converted 50,000 rules to 13,000 rules, but it's not enough, right? It's way too long to check. Let's optimize it even further. So this is a sample rule set of the user. We stripped out the source IP address because we've checked it. And now we're going to put this rule set into another table. We use prefix as a key and protocol and the port sequence as a value. You cannot put protocol and ports to the table as is, so we have to have another step involving these checks. So we have the original procedure with the 13K of rules. Let's add some more steps. And instead of just assigning a user rule number, we are going to add per user table and look up the prefix in this table. And when we find a match there, we are going to check ports and protocols there. Let's take a look on this example. So this is a small rule set comprising five firewall rules. And we can load it into the Radix tree, the normal structure for prefixes. But if we do it the way we used to do, there's a problem. If we make a lookup in the table, we are going to find a more specific prefix in the table or in the Radix. And to make it right, to filter the traffic properly, we need to pull all the protocols and ports down to the leaves of the tree. So we take a TCP/22 port and push it down one level. Then we do the same thing for the next levels, etc., etc., etc. So at the bottom of the tree, all the leaves have all the protocols and ports from their parents. This way, we can do filtering with a single table lookup. Let's take a look how we do it. First thing, we're going to strip out the prefixes, and we are going to rewrite protocol and port check without any IP addresses. We number them, so we make an index for that. And this allows us to create a user table. Let's take a look for that. So this is a set of rules that check for protocol and ports. And this is the per user table as it should be written. So we have prefix in the key and the rule number to check protocol and ports as a value. And now we need a glue. Glue is simple. Take a destination IP address, make a lookup in the table, and do skip to. That allows us to convert the whole rule set to another structure. We have not 500 million of rules, but we have 570 million of table entries in the firewall rule set. And we don't have that amount of rules in the rule set itself. It's not that good, but still it's a way to go. That was one of the first implementations we were running in production. It was like, I think, 8 years ago. So that was done. And what we're going to do, we're going to take a look how we can push the total amount of table entries down. To do that, we can remember that most of the rules are done for the big groups of users, mostly the whole company. And if we have like 65,000 employees, then these 5 rules will get us more than 300,000 table entries. And that is actually a thing to be optimized. If we're talking about smaller groups, well, it's still 25,000 entries, and that's not an option for us. To fix that, what we're going to do, we are going to convert the big groups, the big groups that are referenced in the rule set into pseudo users. Well, just to change the asterisk, just add with a % sign, and now we have converted old stuff DPT all group into a user, and DPT devs is also a user as well. We left the project 1 group as a group, so it will be expanded to the per user rule sets. But okay, we've done that. We do not have any kind of a way to reference the new pseudo users we've created to the real users rule set. To do that, we need some loops in the Ipfw logic. You cannot write a for loop there, so we're going to use strictly written with the finite amount of cycles. So we're going to spell it out. Rule set that allows us to check another user if we do not found a match in the per user table or we didn't find a match in the protocol and ports. So we can go from the per user table or layer 4 decision block back to the user selection. Let's take a look how we do that. First thing, we need to create a rule set for users, including pseudo users. This is a sample rule set for the pseudo user called dpt-all. This is a set of rules that we need for configuring the checking protocols and ports here. Take a look on the last rule action for the real user and the pseudo users. We use different things. We use deny for the real users and return next rule for the pseudo user. Let's do the rule set. The first thing we are going to do, we create a table. Yeah. Table is used to convert mark to real number for each real user. Okay, now we create another table. Another table tells that user with this mark should be checked against a dpt-all or on other pseudo user that is when the user is a member of this group. Basically, what we can do as much tables as we want. So we can add more pseudo users to real user rule set. Let's compile this all together. We create a rule set that checks for the per user table. We create a set of tables that are responsible for converting mark to the rule set numbers to skip or to call. And we need a special thing we call table walker that is responsible for looking up mark and choosing where to jump into the rule set. That is the way, basically, how we converted all these entries down to 25 million of table entries in our rule set. And this is the VM-stat from real production server. There are about 48,000 users loaded into the kernel, and our rule set takes about 2 GB of RAM. There are 17 million of table entries there. This technique has some limitations, though. One is obvious. Every time you want to add a pseudo user to a user rule set, you are going to add an additional table lookup, and it will cost you some CPU power. So you don't want to convert very small groups. You want to convert only large groups to pseudo users. Here's some tips for you if you want to build this kind of rule sets. First thing to think about is to check one packet header item once. So if you take a source IP address, check it once, assign a mark, and use mark afterwards. As we know, rule sets, inserts, and deletions are slow. Keep the rule sets as small as possible. Well, we do have like 100,000 of rules. We consider it not that small firewall rule set, but still. Keeping the firewall rule set small with the help of tables, and you know what? Mark rules, use it. Any questions?
So we Three microphones. Is your IPFW hooked both on input and output, or unhooked at one direction?
This rule set is set on input.
Input only.
Input only. So clear. Oh.
How long does it take to rebuild this in memory from a cold boot?
These days we use loading users on demand. So the whole procedure from 0 to IPFW is capable of filtering the connected users is about 10 or 15 seconds.
How do you expire users out of the table? Is that
Pardon
also,
me?
How do you expire users out of the table?
Yep.
Is that done with Radius as well? Or
It could be done by Radius. You can track the user's traffic and know that there is no traffic from user. You can reload it, unload it.
is Radius used for 802.1x?
Yep.
Okay.
Anyone else?
When you answered the question on the loading time, you aren't doing this using IPFW from /bin/IPFW, right?
Yeah. What we do actually, we push the rules using this bin IPFW, but all the tables are loaded through the EOCatl.
Are you using IPv6 exclusively?
Not exclusively, but we treat any network with IPv6 broken as broken.
So you said you're only doing UDP and TCP. How do you handle ICMP? Because just dropping ICMP can create some problems with IPv6.
Okay. This is very simple. We allow most of ICMP without any dynamic rules. So this is kind of, it is branching prior jumping into the dynamic firewall.
All right, am I missing anyone? Going once, going twice. Thank you very much for this presentation.